Okay, welcome to lesson 3 of this first unit. So we're going to be talking about domain and range. We already started talking about this last day, and so we're just going to kind of continue on this situation now. A big part of this is going to be notation, and so that's the hardest thing that students have with this, in addition to visualizing what the equation looks like. And so you'll have practice doing both of those. And so I just want to start off with this warm up, and you can think about it and read what this might mean. So you've seen these operators a long time ago, and so what these may basically mean is the bigger number is getting eaten by the Pac-Man or whatever. If you draw a Pac-Man symbol around the line, so or it's still an alligator is eating the bigger number, but it's always pointing towards the arrow would be pointing towards a smaller, it's open up to the bigger number. And so which ones are likely correct? Well, if you look at this question, you can say, this makes sense, you're less than or equal to 5 and you're greater than or equal to -3. That's possible, so that could be correct. This number is greater than or equal to -3 and less than or equal to 5, and that's the same thing, so potentially 1 and 3 are the same answer. Number 2 is actually, if you look at it, you can say that x is smaller than -3, but it's bigger than 5. That's impossible. The second one doesn't make sense, so we can say that the second one is potentially impossible. And what might the graph look like? You can just draw like -3 and 5 as a number line. It's really just any kind of function that goes between -3 and 5. So we want to start off with starting with types of numbers. The curriculum, this is not a big emphasis in the curriculum, but I just wanted to make sure that at some point in your mathematical career you do see this. And so it's really important to kind of look at it. And so first, this is called a Venn diagram. The first set inside the Venn diagram is the natural numbers. They're the numbers that were invented first. It's what cavemen used to keep track of something. They started with tallies, then it's just numbers on the wall, 1, 2, 3. I think there's a number system very early that generated 1, 2, 3 in a special way, and I talk about that more in class. And it's based on the angles where the numbers 1, 2, 3 come from. 1, 2, 3, 4, 5. The next one is really just because with natural numbers, we also wanted to verify or just confirm the existence of a zero. So how do you say 0? Usually that means there's nothing there, but we add in 0 for whole numbers. You can remember whole because it starts with an O. And the number sets are always drawn like this, just with a double line on the first line in the letter. The next thing that we needed was whole numbers. Then that kind of went to the existence of negative numbers, and so the word, since it was a German idea originally, the word integer, the symbol for integer is a Z for Zahlen, and it's just the German word for number. So they're saying that numbers are negative numbers included, and so we use the letter Z. We could also use the letter I, but we'll try to use the letter Z in this class. Q is a rational number, so it's the quotient of any two integers is a rational number. So if you take any two integers and divide them, you get what we call the rational numbers. Usually it means like a repeating or a terminating decimal. So if you notice, if you divide any two numbers, you always get one of two things happening. The number would repeat itself in some kind of pattern, or it would terminate. And so that's what we call a quotient for Q, or a rational. So the word quotient's from division. Then we have the irrationals, so we just use the symbol Q with a prime. So it really means not Q. And so examples of irrational numbers are numbers that couldn't be written as fractions, and we just need them to actually describe them. And so the number pi is an irrational number. The square root of 2 is an irrational number. It's a great story about Pythagoras and the invention of irrational numbers. How he had a student killed for proving that the irrational numbers exist. Very interesting. And then we have the real numbers, so it's R, and that's really every number you can think of. So it's all numbers included are real numbers. And the reason why we call them real numbers is because we do have imaginary numbers. There's a problem with taking the square root of a negative, which we've seen before, and we call those complex numbers. It allows you to keep going with number sets. We just use a variable for the square root of a negative, and then we'll see that, we've seen that's impossible. We don't see complex numbers in this curriculum. You'd see that if you went on in math after high school. So mostly when we say all numbers, we mean all real numbers. We will see these with integers as well. You can see wholes and naturals in this lesson as well. So set notation is a way to describe it without actually using words. We're gonna use symbols. So we say like x is an element of the real numbers. So we've got the variables an element of the number set, such that like we're between -3 and 5. This is a logical interval goes there. It's really the restriction that we're providing. It's written in the most efficient way as possible. We'll see it differently when we learn the rational function. We will learn like how to write the domain range for that. Is we just say that x cannot be a number, but this is kind of your restriction where x can lie. And that's just a review from yesterday. Yesterday, we domain is all x values and range is all y values. Just spelt that wrong there. It's all the dependent. Okay. Just a couple examples. We got a parabola to start with. The domain is x an element of the reals because it could be any real number. And then we don't actually use this section here. So we just write x an element of the reals and we close the bracket. We use a curly bracket to state that because x can go on forever in both directions. Range is y is an element of the reals because it's all real numbers. Greater than or equal to -2. So it's anything bigger than or equal to -2. You can put the -2 on the left. It doesn't really matter as long as the alligator is pointing to the y value. Next one is a straight line. We don't have to see arrows. If you ever see this go to the end of the graph, we're just going to assume that it goes on forever in both directions. On a test, I would show arrows, but if you don't see those, and they go right to the graph, you can assume that they go on forever. So x an element of the reals, and then we don't use the second part, and y is an element of the reals, and we don't use the second part. Okay? Because x can be anything, and y can be anything as well. We would just solve for x. In the next one, we could say x an element of the integers, because all integers between -1 and 3. And then range would be y, because y starts at 0 and goes to 4. Y is all whole numbers less than or equal to 4. And so that's just an efficient way to write it. You could also say that y is all integers between 0 and 4. You can see that this is a little bit easier to write if you see that. But don't worry, like you can always say it like this as well. It's just another way to describe it. Or since there's only so many of them, you could just list them. 0, 1, 2, 3, 4. You could argue that this is just as efficient. It's not the way you would want to do it if it went to like 100, but you could do it in this case. So just wanted to show you a few different ways to write the same thing. In a mapping diagram, we say that x is an element of just these 3 numbers. So we could say integers between 3 and 5. That's a lot of writing for just writing 3 numbers. We note that the 6 is not part of the function. It's an input. It doesn't have an output. We can put any number in this first circle, and just if it doesn't have an output, then it's not part of the domain. That's a key, because I could sub in 50, but I don't get anything out. Think about a square root. If we sub in -2 to a square root, it's not part of the domain because you don't get an answer out. And the range is an element of 8, 9, and 12. So y is in 8, 9, and 12. So this e just means y is in. Okay, your practice, you would do this on your own and try and then check the solutions, but I'll just walk through the solutions. The first one's whole numbers less than or equal to 5. Y is an element of 1, 2, 4, 7, 11, and 16. There's no pattern. We can't say that it's all numbers between, so we just list them. Again, you could just list these ones, say 0, 1, 2, 3, 4, 5, but it's kind of neat to write it that way as well. The second one, domain, is all natural numbers less than or equal to 6, because remember that natural numbers will naturally end at 1, or start at 1, so we can say all natural numbers less than or equal to 6. Or you could just list them 1, 2, 3, 4, 5, 6. You could also say all integers between 1 and 6. And the range, again, no pattern, so we just list them. The next one is a line that starts clearly at -1 and then goes on forever. So it's greater than or equal to -1, all real numbers. The range starts at 0 and goes on up forever. And so even though there's no arrow, it just goes to the end of the graph, so we assume it goes forever. If you said that it stopped at 6, that would be correct, but this is just easier to say that it goes forever. Next one is a parabola. A domain's all real numbers, and the range is less than or equal to 3. This is a straight line that starts and ends, so we have to say it starts at 0 and ends at 8, and it's all real numbers because it's not like points. It's a connected solid line. So pi, for example, is in there, right? And like decimal numbers are in there. Everything is in there. Range is similar. It starts at -2 and ends at 2. The next one is very similar to that. It goes from -2 to 4 and -1 to +15. The next one's all integers between -6 and -3. You could also just say -6, -5, -4, -3, like we would in the second one. So you could just list them out, and that would be just as efficient because there's only 4 numbers to list. The last one is a dotted line. So what a dotted line means is it's just symbolic of not every number between, but on forever. Because we don't, it's going to be the integers, so just on the whole numbers. But the reason why we do a dotted line is because we want to assume that it's going on forever, and so we can't do it like this one over here with just points on the integers, because that would then we wouldn't have a way to go on forever. So this is a dotted line. It's just all integers for both the domain and the range. Okay, and there you got some practice.